Cool. Alrighty, so let's start with arc length. All right, so we know that if you have a curve and we want to look at a differential amount of length along that curve, which your professors call ds, we have various formulas depending on how the curve is given. So if y is a function of x, we know that ds would be 1 plus the derivative of y with respect to x squared dx, right? Y is a function of x. If we're going to be doing integration, we're going to end up integrating with respect to x because y is a function of x. In the case where x is a function of y, not a different formula, right? It's just that we're going to end up integrating with respect to y, and then we'd be differentiating x with respect to y because it's x that's a function of y. So we're integrating with respect to y, so we're going to get a dy in there. Okay. And then if x and y are both functions of a parameter, which I'm going to call t, so that's the parametric stuff. Doesn't have to be t. Right, we're just going to differentiate both x and y with respect to the parameter t. I guess I can write it this way and square those and add square root, right? It's just a application of the Pythagorean theorem in calculus. And of course, we're going to be integrating with respect to the parameter, whether it be t or theta, whatever. Yes? Oh, I'm just writing the differential length element. You're correct that arc length, let me just go ahead and write that. Thanks. So arc length in general, right, is just the addition of these little differential length elements along a curve to get the total length. So yes, you're going to be integrating. So for example, if you have y as a function of x, you're going to be integrating ds, as we formulated there. And you're going to be integrating with respect to x, so your bounds will have to be x bounds. That's correct. I'm just writing the differential right now, and then we're going to find the integral of that. Okay. And finally, polar. So that's where an r is a function of theta, and we know in the background x is r cosine, y is r sine. As it turns out, it's essentially a parametric curve, right? Because the parameter is theta. And if you do the calculus, you're going to find that ds simplifies to the derivative of r with respect to theta squared plus r squared. And then since the parameter is theta, we're going to have d theta in there. Okay. So those are all the cases that I can recall. Okay. All right, so let's do some examples. And again, you can stop me and ask about anything on that review that was posted. Yes? If it's not clear, I apologize, but that's x prime, right? Derivative of x with respect to t squared plus y prime. Again, I'm not sure if that's clear again. Or if I can rewrite it, maybe I can write it as derivative of x with respect to the parameter squared plus the derivative of y with respect to the parameter squared. Okay. So somebody wanted to go over the 6 main topics. I'll just flash that on the screen. but we have arc length, area of surface of revolution, calculus of parametric curves like differential calculus of polar curves, area, I guess, under polar curves, so to speak, right? And sequences. All right. Cool. All right, so first example is where y is a function of x. And right, we'll go ahead and write down the bounds as well. We're going to limit this where x is between 1 and e. And I don't know how to graph this exactly, but it's a parabola vying for attention with a log function. So, all right. So we said the arc length is going to be the integral of ds. We're adding up the little length elements. Because y is a function of x, we're going to differentiate y with respect to x. And then we're going to square that and add 1, right? I'm looking at you there. Oh, no, that's the wrong one. I'm looking at you. Right. Okay, so if they really want you to get a number answer, not just set up an integral, they have to give you something that's integrable. So in these cases, you're either going to get a perfect square or you're going to get something where you can use a u sub because you're going to get a square root. Okay. All right. So you have faith that if they want you to get a numerical answer, you will. Does everybody see how I get 1/2 here when I FOIL that out? Or should I write it out?
Yes.
Yes, what? Yeah, okay, thank you.
Yeah, I mean, you can write it out. Let's see.
Oh, right, I will. Okay, so I'll go back and FOIL it out, but we will get, after FOILing out, a negative 1/2, and then there's a +1 from the formula. So adding those two constants, you get a +1/2. Okay. So let us go ahead and FOIL that out really quick. So I'm going to revert to, what is this? What kind of ink is this? Okay. All right, so we FOIL the business out. There you go. I don't need glitter in the ink. Right, so when you multiply those out, of course, you get a negative, and you get 2x times 1/8 x squared, but then you get exactly the same term when you multiply the insides together. And finally, negative times negative is positive 8 squared x squared in the denominator. So these two middle terms will combine, all right? We have some simplifications, xx, xx, and you get negative 1/4 minus a negative 1/4, so that gave you a negative 1/2. And that's where I got that negative 1/2 from. Right. So then we anticipate that we're going to be taking the square root of this expression right here. So this, if we're going to, well, we could use trig sub and stuff, but it turns out to be a perfect square by design. So does anybody see how to factor that? All right. Well, one thing we can always try, if you're not sure, you know, and you have a bunch of terms, maybe you can try to combine them to a single fraction. But notice that the two outside terms, we can think of as like 2x squared, yeah, for the 4x squared. And the outside term is like 1 over 8x quantity squared, right? So, and the middle term is positive. So it turns out that we put a plus here, and it factors. So that's often you see that. I think I saw that in 2 of the problems on the paper review that your professors posted. Okay. If you didn't see that, I guess you can always try to get a common denominator, but that's going to be a kind of a pain because the common denominator would be 64x squared. So you would have to multiply the top and bottom here by 16, right? 40 and 20, yeah. Well, no, 16x squared. So, what do we need to introduce the common denominator? Wait a minute, 64 times 4. Oh, that's awful. So 4 times 64, x to the 4th. And here we would multiply the bottom by, for the middle term, by 32x squared. And then we have the third term. So now that we have a common denominator, okay, and this is not really easier because you still have to notice that this is a perfect square in the numerator. Okay. Right, that would be 2 times 32, no, 2 times 8 is 16, plus 1 squared. You can confirm that that works. All right. But in any case, either whichever approach you took, these are equivalent, by the way. Just one is separated into 3 fractions. Right. Once we have that, we take the square root, and we're given the x bounds are from 1 to e. All right. But either way, if we get it, we can think of it this way, right? So then we have a square root of something squared, and just to be sure, if this comes up, what's the square root of something squared in calculus? Well, just in general. So recall that the square root of something squared is the absolute value of that thing. It might come up in some problems that I saw in polar curves, but right. Here it doesn't really matter. Maybe that's just a detail you don't want to worry about too much, but you know, then you might not get 100 or something. But here we're integrating over an interval of x's from 1 to e, where the thing inside the square root, the thing inside the absolute value would be positive anyway, right? Everything would be positive. So we know if the thing inside the absolute value is positive, we just drop the absolute value. Let me rewrite that. Right. So if the thing inside the absolute value is positive, just drop the absolute value bars. You don't need them anyway. But if the thing inside is negative, what do? Well, we drop the absolute value bars, but then we just say that if we negate the negative value, negate the negative value, then we would get the positive, which the absolute value would guarantee. So it's a trade-off, right, for a single expression of absolute value for cases where we can do maybe easier algebra. So if somebody's asking online what happened to this 1, well, I combined it with this negative half to get a positive half, and then I factor. Okay. So anyway, we can drop the absolute value bars here, just to make sure you're aware. And then we anti-differentiate. And plug in the bounds. So, okay, you get some interesting answer, right? Okay. We'll come back to that when looking at surface area. Oh, this is polar. So, example 2. We were able to drop the absolute bars because the thing inside is guaranteed to be positive. Right? This is positive when x is between 1 and e. Because you just have positive numbers and you're adding them, you're multiplying positive numbers. So since this was positive, we can just drop the absolute value bars. Okay, so maybe I won't do this one, but I'll write it down so I can make sure that I typeset it later. I guess I can make a equal 1/12. Yeah. But just an example. Where we have a function of y instead. Okay. Okay. And so here, the arc length, we would have some bounds for y because we have a function of y. And then we have ds. When we have a function of y, that's just 1 plus the derivative of that function of y squared. And you're integrating with respect to y. Okay. So it's really the same, very similar problem. So if you want to practice that, you would differentiate y, or the function of y. We would square that derivative. So you would have to FOIL. Do they still call it foiling? And then when you multiply these, the two terms, you get a negative quarter, but there's two of them, right? Because you can multiply the first term with the second, and when you FOIL the second with the first, but you get exactly the same thing. So same story. Okay. Well, I didn't give you the y bounds, did I? It doesn't matter. Let's say -2 to 1. So suppose y is between -2. Is that even legal? Yeah, it's legal. We can't divide by 0, but All right, then we have the square root of 1 plus this derivative of f squared. That looks sloppy. And then you have the plus 1 from the formula. Okay. Right, again, the constant terms will combine to give you a positive 1/2. And you get another perfect square, really the same type of problem as the previous one. Okay. Yeah, well, for people in chat, yeah, we'll get to a problem where the thing you're taking, you have absolute value of something that might be negative. We'll look at that. Okay, but that's a perfect square. Can anybody tell me what that perfect square is just by inspection? Yes. Which one? The negative half and the 1? Oh, I made that up. It's just given. Like in your review, it's just given. Yeah. But you would have to have like this, if you were to FOIL this squared business, you should get 1/16 y to the 4th. So it's natural to guess that you get y squared over 4, because if you square that, right, then you get a plus. And then you look at that and you say, oh, what's this? What would give me 1 over y to the 4? It would be 1 over y squared after you FOIL. And if you'd want to practice, try maybe combining the 3 terms here underneath the square root into a single term to see if you see the hidden perfect square better. Right? And so we get square root of something becomes the absolute value of that thing. And can we drop the absolute value bars here? Sure. What the thing inside is positive. And how do we know it's positive? Even though the y values we're integrating over are negative, because we have y squared everywhere, right? That's never negative. All right. And then it's just set up for the power rule, right? So we're going to get a 12th of y cubed and minus 1 over y, as y goes from -2 to -1. And I don't know. I don't care what that. That's some number. Right? Awesome. So let's now go to, I'll come back to that as well. Let's look at a parametric thing, parametric curve. Cool. So the third example. Let's do x is a function of parameter t. It's equal to 2 cosine cubed, and y is 3 squared of t. Let's say t goes from 0 2 pi. And we're again asked for arc length, right? The length of the curve. Okay. This time, x and y are given parametrically, so we know the differential length element along that curve is the square root of dx dt squared plus dy dt squared. And we'll be integrating with respect to the parameter t. And we see our bounds as well from 0 to pi. Okay. I guess they could be tricky, right? Like, how can they make this problem harder? Like, how is it possible that they might not give you the bounds? Right, they might say, find the arc length as we start from the point 2, 0 to the point on the graph, which is -2, 0. Right, then you would have to figure out the bounds for t. Right, it's just you to say, well, x is 2 at the starting point, and y is 0 at the starting point. So then you would try to find a value of the parameter that satisfies those two equations. So cosine cubed is +1, so t must be an even integer multiple of pi, but cosine is 0. Okay, well, t is a multiple of pi. So we just choose, like, let's the starting point is t equals 0, right? That works. And then at the ending point, we need cosine cubed to be -1, and we need sine to be 0 again. So the next value of t where this is true would be where t equals pi. So I guess technically you could figure that out. Okay. Like 2 consecutive values of t. Well, yeah. Anyway, so let's differentiate. Maybe we should just work with this for now. Right, derivative of x with respect to t. We all know that this is a chain rule. And then derivative of y with respect to t, chain rule. Okay. Oops. Cosine squared squared is cosine to the power 4. All right, and then we're going to be taking the square root of the business as well. Okay, and it looks like we can factor some stuff out. What's common here? 36. We have a couple of cosines in both terms, and we have a couple of sines in both terms. So if you're not sure what to do, if you don't see a perfect square, maybe try to see if you can factor something common out. So cosine squared and sine squared can be factored out, leaving behind cosine squared plus sine squared. Okay. And everybody should rejoice when they see this, of course. That's 1, Pythagorean trig identity. And so what should I write here? Well, square root of 36 is a +6. And then we have square root of cosine times, square root of cosine squared, square root of sine squared becomes the absolute value of cosine sine. Is that okay? Well, okay. Even though we love to see the Pythagorean trig identity, it's kind of like that crush you see around the corner, but it's not actually them. I apologize for that. You're absolutely right. Okay. So correct. So let me back up. Thank you for catching that. So we would be left with a cosine squared, and we took every term out of here, so we're left with a 1, right? Thank you. So now that would be 6 absolute value of cosine t sine t. And then we still have the square root of cosine squared plus 1. Okay, now we're going to have to integrate that. So does that look doable? So it's a parametrization with respect to t, so our integral is with respect to t as well. Okay, so can we drop the absolute value bars here? Let's just think about, the xy plane, and we're integrating. Let's think of t as theta. I could have used theta, but think of t going from 0 to pi. And would you say cosine times sine is positive or negative in the first quadrant? Sine times cosine. It would be positive, right? Because both sine and cosine are positive. What about quadrant 2? Would sine times cosine be positive or negative? It would be negative because cosine is negative and sine is positive in the second quadrant. Right. So I can't just drop the absolute value bars because we have two cases. So we could instead just integrate or break up the integral from 0 to pi over 2. So we're kind of strategizing that integrating over the first quadrant, right, would give you a positive thing. So we can just drop the absolute value bars. And then we can integrate from pi over 2 to pi for the remainder. But this time, sine times cosine is negative. So we would drop the absolute value bars, but we would negate the thing that's known to be negative, so we get a positive. Oops. Okay, but in any case, by symmetry, by the way, these two integrals should be equal. And if you're doing arc length or surface area, you get a negative number. Is that possible? No, just to make sure you see. Yes. Because we are integrating, if you look at t, we're integrating on the as t goes from 0 to pi. But we decided to break that up into two separate integrals. One integral is from 0 to pi over 2. The next integral, so that's integral 1, and the next integral was from pi over 2 to pi, because we had that absolute value. Yeah. Okay. And then we can just, it's a simple U, it's a U sub. Do you see it? Yeah. So if we just focus on the antiderivative, if they want you to integrate, there has to. So this is the case. You don't get a perfect square, but you're able to factor something out, take the square root of it, and then it's set up for a U substitution. So just let the thing inside the square root be the U, and hope for the best. Right. So du is 2 cosine times the derivative of cosine negative sign dt. Okay. So multiply both sides, say by -3, to complete the change of variable, right? So we have that this business is -3 times du, and this business is just u. Right? So we get -3 square root of u du. Anti-differentiate. So, okay. So, all right, yeah. And then back substitute, I suppose. Okay, and then you can plug in the bounds, right? We have the antiderivative, and zero to pi over 2. It's the first integral. And then we would have essentially the same antiderivatives that would be positive. And we have those other bounds from pi over 2 to pi. And then plug and play. So you get -1/2 at the, and then you get +1/2 times 2 to the power 3/2. Oops. All right. So indeed, these two integrals by symmetry gave you the same amount of length. You just double it up. So you get a nice answer, satisfying answer. Oh. Okay. What is, somebody mentioned the odd cosine rule? I would have to refresh my memory on what that means exactly. I know cosine is odd. Somebody mentioned the odd cosine rule. Okay. All right. So that's an example of arc length with parametric curve. And do you want to do one with polar curve as well, just as a reminder? All right. Well, do I really have time for that? I'll just try it. Okay, so I believe this would be example number 4. Yeah. So here we're given a polar curve. Whatever. I believe there's a similar one on the paper review from your professors. It's kind of a standard thing. So remember that the differential length element when dealing with polar curves was r prime. So derivative with respect to theta squared plus r squared, and then parameter is theta. Right, so the derivative here would be 2 cosine negative sine and don't forget that triple chain rule, right? And then we still have to multiply by the derivative of the inside theta divided by 2. The derivative of that is 1/2. All right. Then we plug that into our differential length element formula for polar. So r prime squared and plus r squared. So I think it's a very similar type of problem. D theta. Because we can factor out a cosine squared. Yeah, it's not too dissimilar, right? Here we have absolute value of cosine. All right, so then we would need to integrate, or if you'd like, add up. Does anybody, I always this question, I'm sure people are getting tired. Does everybody know what the symbol originally meant, what letter that was? When Leibniz wrote that integral symbol, do you know what letter Leibniz was? Yes, S, because you're summing up stuff, right? It's a geometrical kind of interpretation. But you're summing up in this kind of calculus continuous limiting fashion. And the bounds were from 0 to pi as well. So I guess if theta is between 0 and pi, we want to focus on this theta divided by 2. So we're going to divide everything by 2. And we see that theta divided by 2 would be between 0 and pi over 2. So is cosine of theta divided by 2, when theta divided by 2 is in the first quadrant, going to be positive or negative? It's positive. So we know we're safe to drop the absolute value bars. And then we anti-differentiate. And I guess, well, I don't know. That's a great question. How to actually integrate this, right? I don't know. I guess a U sub followed by a trig sub or something. So I'm not going to bother. But if you'd like, you can try it. So U sub followed by, you're going to get something like the integral of u squared plus 1, or square root of u squared plus 1. So you might try a u sub, and you might a trig sub, and you probably get something like secant cubed. That off my least favorite integral that I see in the lab is secant cubed, because you have to explain it. But you would get secant if u is tangent, du would be secant squared. So yeah, you would get the integral of secant cubed of some form. So try that. U sub followed by trig sub. All right, so the next topic, if you're okay to move on.
I have a question.
Yes.
In example 3, when you did the U sub, shouldn't it be
You cut off.
negative 2 times cos squared t plus 1 or something?
Well, all right, or something, so can't disagree. I don't see any mistakes so far.
When it says negative 3 times u to the power 3 by 2 and then divided by 3 by 2, when you're multiplying 2 by 3 to the numerator, sure, it will cancel the 3. That's what I was thinking.
Oh, I see what you... So you're saying this should be times 2, I think, is what you're saying. Right over here?
Yeah.
You're right. I messed up the flippity flop, you know, the reciprocal of the reciprocal, go figure. Yeah. You are absolutely correct. All right.
I have a
Is
question.
that what you meant?
Hello?
Was that what you meant?
Yeah.
Okay, thank you. Oh, well. All right, so anyway, what would be 2? Okay, so thank you. All right. So the next topic was area of a OOF surface of revolution. Okay. So for that, just remember some basic rules. When you revolve a curve about some axis, your cross sections are circles. And so for given value, cross section is a circle. You have a radius, and then we would want the circumference of that circle. We know circumference is 2 pi r. Okay. And then what we would do is multiply that little circumference by a length along the curve ds, which would give us a differential volume element. It's like a differential amount of volume of a ring, you know. And then we're just going to add it all up. So, okay. So then we integrate. Yeah. So this would give you the general formula for the area from a surface of revolution about some axis. Circumference times length gives you the differential area of a ring, if you will, and then you add it all up when you integrate. Okay, we just want to consider the various cases. So the first thing to consider is whether we're going to be rotating the curve about the x-axis or the y-axis. Right, so if you have some curve and you're rotating it about the x-axis, which variable, x or y, would serve as your radius? It's given a value of x, if you draw a cross-sectional, yes, y, and you draw, just take a cross-section, you get a circle, and if you draw the radius, you draw a vertical line, so that's like the height, right? So it's like the y value. So if you're rotating about the x-axis, you're going to get 2 pi y, because y plays the role of the radius. Of course, on the other hand, if you rotate about the y-axis, you take a cross-sectional ring there, you draw a radius, you'd be drawing a horizontal segment, you're moving in the x direction, so it's x that plays the role of the radius there. So you would get 2 pi x. Yes. So that's one thing, one factor, right? Which axis are you rotating about? X-axis, then it's the y variable that plays the role of the radius. But the y-axis, then it's the x variable that plays the role of the radius. Right. And then the second factor would be how this curve is given. Is the curve given where y is a function of x? Is the curve given where x is a function of y? Is the curve given parametrically? Or is it like a polar curve, right? So again, those cases. come up with surface area stuff. So maybe we can organize this information with a table. So, okay, so we have the axis of around which we're rotating. And then we can consider the cases where y is a function of x. Okay, so here we would get around the x-axis, we know that y plays the role of the radius. So, and because y is a function of x, ds is going to look like 1 plus f prime squared, just as before, yeah, in arc length. And then because we have a function of x, we're going to be integrating with respect to x, so the bounds will be x values. So notice that here we would replace y, because we're integrating with respect to x, so we only better see x's. So you're going to replace y with this function of x. Okay, y-axis. So this time the radius is played by x, but y is still a function of x, so our differential length element ds is still the same formula. And sorry about that. And we'd be integrating with respect to x. So what you want to notice about this is since we're integrating with respect to x because y is a function of x, we don't need to replace x with anything because you're already integrating with respect to x. So it's just x. Over here we had to replace y with whatever it is equal to as a function of x. Okay. So now suppose x is a function of y instead, and you're rotating about the x-axis still. So your circumference is 2 pi y. And because x is a function of y, we'll be integrating with respect to y, and we'll be using that ds formula when x is a function of y. Okay, right, and we're integrating with respect to y, therefore bounds are y values, and there's no need to replace this y with anything because we're integrating with respect to y. Okay, 2 pi. So this time we're going to rotate about the y-axis, so we get x, 2 pi x, but x is still a function of y. Right, and we're integrating with respect to y, so the bounds are y values. And do we need to replace x with anything? Absolutely, right? We're integrating with respect to y, therefore we only want to see y variables at the end of the day. And we get to replace x with a function of y. Okay, so what about parametric curves? Right, it's the same, right? Except our ds is going to look different. Right? You get 2 pi y if you rotate about the x-axis, but you have x and y are functions of parameter, say t. So ds, as we know, will look like that. And of course, you would replace y with whatever is equal to in terms of the parameter. Likewise, here you would have to replace x with whatever it's equal to in terms of the parameter. Anyway, I'm just trying to think about how to organize this. This is kind of mental preparation you should be doing, right? Going through all the cases and thinking to yourself, can I organize this in my head? And then, of course, there's polar. Yeah, just the ds is going to look different. Okay. I'm running out of space here, so it doesn't let me scroll to the left or right. That's interesting. Okay. All right, anyway, let's do some examples. All right. So I believe this would be example number 5, 6. Okay, thank you. So really just about setting it up. So it's not going to be a new function right here. Y is a function of x. And suppose you want to set up that integral and you can evaluate its practice. Suppose we're going to find the area of the surface of revolution by rotating about the x-axis, or yeah, x-axis. Right. So since you can always motivate which variable should play the role of the radius by drawing some curve rotating about the x-axis, cross-section, the radius looks like it's a vertical segment, so that would be played by the y variable. So you get 2 pi y and I think x, x is still from 1 to e as before. So 2 pi y ds. All right. Since y is a function of x, we're going to end up integrating with respect to x. So the bounds will be x values. And we're going to end up integrating with respect to x. So y needs to be replaced with a function of x so that we only have x's in our integrand. And we know ds, when y is a function of x, is 1 plus the derivative of y with respect to x. All right, and so that's the setup. I think, yeah. And this would be an exercise of an integration by parts and u substitution. I believe when we did this, we got a perfect square. The square root it was positive, so I think that turned out to be 2x. So this is like from problem 1 or 2 or something. You got this. So you would distribute and integrate term by term. I believe you would get like log of x times x or something. So that's the integration by parts. Okay. All right. What if instead you took the same curve but rotated about the y-axis this time? Right, and x is still from between 1 and e. Well, right, again, forget exactly which variable plays the role of the radius here. Just draw some stand-in curve, rotate about the y-axis. Cross-sectional circle has a radius that's horizontal, so that x plays the role of the radius. So 2 pi x. And then we still would have the differential length element when y is a function of x. And since we have y as a function of x, we'll be integrating with respect to x. So the bounds are x values. And this time, there is no need to replace x because we are integrating with respect to x. no mixed variables, right? And then we already computed this business above. So now it's just an exercise in integration. Distribute the x inside the parentheses, so on and so forth. Whatever that turns out to be. Okay. Cool. Okay. Let's see. Let's do one that's maybe parametric. It's really polar in disguise, right? Yeah, let's try it. So this will be both kind of parametric and polar, even though you might. All right, so we could think of it as parametric, where you have x as a function of parameter theta. Let's say x is 2 times cosine squared of theta, and y is 2 cosine theta sine theta. Okay. Theta is going to go from 0 to pi. Do you see why this is also polar, really? So this is parametric, but he could have easily done an example where r is cosine theta, right? And y are those 2 times cosine, sorry. So that would be polar. And we know it's the same thing because x is r cosine. So if r is 2 cosine, then x would be 2 cosine cosine, so cosine squared. And y would be r sine. So 2 cosine sine. So it's really kind of the same thing as polar. So you can take either approach. But suppose we want the area of surface of revolution, and you rotate about which integral would be easier to do, right? Let's say x-axis. Right. So we get 2 pi, and which variable plays the role of the radius? Y. Right. But since it's a parametric curve, the parameter being theta, we have to replace y in terms of theta. And then we would need to multiply, right? But you have to differentiate x with respect to the parameter squared. Okay. This would be our ds. Differentiating x. Differentiating y. I probably could have used some identities there to simplify matters, but derivative of y with respect to theta, so that would be 2 cosine squared minus 2 sine squared d theta. Does that simplify, you think? I think. What do you think that simplifies to? 2 theta. Does anybody see why this simplifies besides just multiplying out, right? So remember the identities. So we call the identity where 2 sine cosine is the same as sine double the angle, and then cosine squared minus sine squared is cosine double the angle. So that might save us some time. So these are just some trig identities. Yes, you rang? All right. All right, so we can rewrite this as 2 sine 2 theta squared. Oops. Plus, and then this would be 2 times, forgot, double the angle. Right, because that now reduces, correct? What does that reduce to? Well, we have the Pythagorean trig identity. Factor out of 4 and you get cosine squared plus sine squared of the same argument. So you just be left with square root of 4. So yeah, this reduces. Pyth trig ident. Right, Pythagorean trig identity. Beautiful. Maybe I should write it out. And then that's just a simple either substitution or, again, trig identity. What were the bounds? Oh. So let's see. So that would be 4 pi sine squared theta. Which doesn't sound right, because you get arc length of 0. So what happened there? Well, that can't be right. Arc length can't be 0, right? Four cosine sine. Cosine squared minus sine squared. 2. Well, x and y. Somebody asked if what happens if x and y have different domains. Well, no, it's they're both functions of parameter theta. I'm not sure if that's what you mean. So they would have to have the. Oh yeah, that's when we get to polar curves in area. We'll discuss that. Something went terribly wrong there. If anybody sees it. Beep, beep, beep. What is y? Well, I don't want to dwell on it too much. We said y is 2 cosine sine. Parametric formula. Well, let's see. What if we treat it as polar, just to see if we get the same integrand? So if it were polar, right, we're still rotating about the x-axis, so y still plays the role of the radius. Okay. Right, except we would have to know, we know that y is really, so in polar we said r was 2 cosine. Right? So we know y is really 2 times r times sine. And then the formula for the differential length element in polar was r, the derivative of r with respect to theta squared plus r squared. So that should at least give us the same integral. So what's the derivative of r with respect to theta? Negative 2 sine theta plus r squared. And we said theta goes from 0 to pi. So we did have the Pythagorean trig identity. Oops. What did I do wrong? Maybe I shouldn't. Oh, because y could be negative. Ah, I see the problem, unfortunately. Anyway, I'm not going to dwell on it, but since theta is going from 0 to pi, in the first quadrant, that expression cosine sine is positive, in the second it's negative. So that's an issue. I should have made sure that y is above the x-axis, right? I mean that, yeah, that y is always positive. Okay. So I messed that one up. That's okay. It's okay. We'll fix it. All right. So they probably would have told you to rotate about the y-axis, right? So then it would be 2 pi x ds. Where x is 2 cosine squared. And ds would still be the same as before, so just square root of 4. Do you think that gives me the right answer? Oops, 8. Integral of cosine squared. That's going to be positive, right? Because you're integrating something positive, something squared. And remember, how do you integrate cosine squared? Does anybody remember the identity? Right, there's one for sine squared under power reducing identities. I believe sine squared is 1 minus cosine double the angle, while cosine squared is just the conjugate of that, so 1 plus cosine double the angle. Okay. What's the antiderivative of 1? Oops. And I know what I did. I should have changed the angles. That doesn't make sense. Yeah. And the antiderivative of cosine 2 theta would be 1/2 sine 2 theta. So yeah, cosine at any integer multiple of pi is 0, so that's going to be 0 to either bound. So we're just going to be left with 4 pi times pi. So I just wasn't very careful. I should have either changed the bounds from, let's say, negative pi over 2 to pi over 2 or something. Okay. All right. So that's surface area. And then we have the calculus of parametric curves. So all right, so here x and y are given as functions of a parameter, and we just want to recall some formulas. So for example, dy dx, it's a sort of chain rule. It's the derivative of y with respect to the parameter on top, derivative of x with respect to the parameter on bottom. So this will give us like slope, right, of tangent lines. It's the derivative. And if they ask questions about concavity, we're going to be required to find the second derivative of y with respect to x. So you have to compute the first derivative, and you're going to get a function of t over the parameter t over here. It's a function of parameter. Okay, and you know that the second derivative is nothing but the first derivative of the first derivative, right? So you're going to have a function of t differentiated with respect to x, so you're going to have to use chain rule, differentiate that with respect to, oops, sorry. So using the rule above, I think all you have to do is just differentiate this expression with respect to the parameter t. It's a function of t. It's the derivative with respect to t of the first derivative, which is going to be a function of t. And on the bottom, you still differentiate x with respect to t. So that's a little tricky. It's not what you think it is, right? It is not the second derivative of y with respect to t divided by the second derivative of x with respect to t. That's wrong. Okay. So all right. So given some parametric curves, that's not the one I want. Yeah, this one. So this is example number 7, I believe. So let's just start with kind of polynomials. X and y are polynomials of parameter t. And what kind of things were you asked to do with these parametric curves when, with differential calculus? I think you're asked to find, given a curve, you want to know where or what the horizontal tangents are, and you want to know where or what the vertical tangents are. So that's not a bad jelly bean, right? Or bean. Okay. So we want horizontal and vertical tangents. So do you remember how what definitely guaranteed horizontal tangents? Well, if you have a horizontal line as you move along it, which variable is not changing and which variable is changing? Well, horizontal tangents, you're just moving in the x direction, right? So y wouldn't be changing. So you want dy dt to be 0. And let's say dx dt not be 0. Otherwise, if you look at this formula for the slope, you would get 0 over the 0, which is right now indeterminate. So we're going to have to do closer inspection using limits when that happens. And vertical tangents, similarly, moving up and down, y is changing, but x is not. So that's where dx dt is 0. And for now, we'll just say dy dt is not. Okay, so that guarantees horizontal and vertical tangents. And in the special case, call it the limiting case, because we're going to be taking a limit. So you have like case 1, case 2, and then the limiting case, right? Where both are 0. Right, then we're going to have to look at dy dx as we computed it parametrically, right? Dy over dt, and then dx over dt, and then take a limit as t goes to whatever the the problematic value of t is. So if both x and y have derivatives equal to 0 at the parameter value, you have to take a limit and to investigate further. Okay. All right. So let's go ahead and find vertical and horizontal tangents here for this particular parametric curve. So we're going to be finding dy dt. Okay, so differentiate y with respect to t. And then compute dx dt. Okay. And if you'd like, we can now write down what dy dx is. It's dy dt over, it's the derivative of y over the derivative of x with respect to the parameter. I believe we can factor a bit here in anticipation that probably, well, we want to know where dy dt is 0, right, and where dx dt is 0, so you might as well factor there. What do we get? T squared. All right. Oops. And downstairs we see that we can factor out a 9. And then we get a difference of squares in the denominator, so t minus 2 times t plus 2. All right. All right. All right, so we're on the hunt for well, let's just say dy dt 0. When what is, for which values of t, or values of t, when t is 2, right? We just set that derivative equal to 0, solve for t. And we that dx dt is 0 if t is either positive 2 or negative 2. All right. So there's a clear, is there a clear case of horizontal tangents? Well, no, right? because for a horizontal tangent, we said dy dt is 0, and that happens when t is 2. But dx dt is not, right? But it is 0. So it's actually the third case that we're dealing with there. Okay. All right. So we would have to investigate more closely. We take a limit as t approaches 2 of dy dx. And we've already factored. So we can simplify. And so you get 0 over 0, so you see why that was a problem. So we're going to do the standard thing. Use L'Hopital's or factor. Here we just factored and things canceled out. Right, we had one of the t minus 2 factors canceled with the one in the denominator. And so now we evaluate the limit, and we got 0. Right. Okay, so do we have a horizontal tangent or not? Well, dy dx is 0, right? At the limit at least. So yeah, don't you think? If the derivative of y with respect to x is 0, that means we have horizontal tangents from calculus 1. That's how we found mins and maxes, right? Critical points. Okay. So yes, we have horizontal tangent when t is 2. Okay. And how would you find the equation of that horizontal tangent? Right. What's the equation of any horizontal line in the xy plane? What form does it take? Well, y is constant, right? Constant height, if you will. So how would you find what y is equal to when t is 2? Well, it's not a mystery. There you go. We know what y is as a function of. So it's y at 2. So t cubed, and so on and so forth. Just plug that into your y function. So 12, right? So the equation of that tangent, horizontal tangent, would be y equals 12. Right. Now, on the other hand, we see that we do have a clear case of a vertical tangent, right? Because that's when dx dt is 0, but dy dt is not. Right? Oops. Okay. So we have a vertical tangent when t is negative 2. And a vertical tangent, a vertical line in general, has the form where x equals some constant, right? Because you don't move in the x direction, it's constant. So that's x at negative 2. I'm supposed to remember that? Can't you zoom in and out with this stuff? All right. Okay. 24 plus 72. Does anybody know what that is? It's 70 minus 22, so 48. 48, right? Awesome. Cool. So what other things can they ask you besides horizontal and vertical tangents? Well, they could just ask you for an equation of a tangent line, right? So they could ask you for an equation of tangent line to the parametric curve. Let's say when t equals 1, as an example. Right. So that way, you know that we're going to use point-slope form. Right? And so we need to find a slope and we need to find a point at time equals 1, so to speak. So the point is easy, right? Because that's just what x is at t equals 1 and what y is at t equals 1. And we were given those equations, which I'm just going to copy and scoot over because I'm tired of scrolling. Oh, how do I copy? I should have connected the mouse, right? Just paste. What just happened? Oh, there you go. All right. So the point is not bad. If they give you a value of the parameter, just plug it in for the parameter, and you get that x would be negative 33. Right? I think I know how to subtract. Yeah, 33. And y would be, what is it? 1 minus 6 plus 12 plus 4. So 6, 10, 11. All right. So how do we find the slope? Well, we know slope is nothing but dy dx. And we knew how to compute that parametrically. We just need to evaluate that result specifically when t is 1. I believe that this was 3 t minus 2. We could have just left the simplification in there, but whatever. Right, so we already computed that derivative. Let me just fill it in. So I believe this is negative 1/9. Okay, so that's our slope. Right. Our point, we said, was x is negative 33, y is 11. We have our slope, negative 1/9, so we use the point slope form of the line. And simplify if we want. Oops, what am I doing? 3 times 3. Okay, so that's the equation of the tangent line to the parametric curve at t equals 1. Okay. Of course, they could have also asked you something like, when is the, so instead of asking for horizontal tangent or vertical tangent, they could say, at which values of t is the slope equal to whatever, 1, right? So they could have asked you when, or for what values of t, I'm thinking of t as time, when is slope of tangent line equal to 1? But then you can imagine the way you'd proceed, right? You'd compute the slope, dy dx. You don't, and you want it to equal to the, when is the slope of the tangent line equal to 1? So you just set that slope equal to 1 and solve for t. I don't know what that would be, but you can quickly do that. So at t equals -4, right? Okay, so what else can they do? They could ask you on which, how would they ask, for which values of t is the curve, is y increasing or is it decreasing, right? Or is the graph increasing or decreasing? So that still has to do with dy dt. Sorry, dy dx. And we want to know when it's 0, when it's positive, when it's negative. Okay. Now they could also speak of concavity for the curve. So where is it concave down? When is it concave up? Well, that would entail that we look at the second derivative of y with respect to x. So we'd use the formula for finding the second derivative of y with respect to x when x and y are given parametrically. Right. So we're going to differentiate with respect to t the previous result, which was dy dx. I would have probably simplified before differentiating. Maybe. Would I lose any information? Interesting question. And then divide by dx dt. Which we've already computed, right? Yeah, I'd probably simplify first. Before differentiating. Okay. All right, looks like a quotient rule going on there on top. So you get 4/3. And you can simplify. All right, so what would be like the critical points or the cut points, if you will, right, for values of t? Well, -2 and 2, that's when the denominator is 0 there. And then you just choose test points. Okay. So you choose test points to test concavity. So maybe we can choose like -3 or something. Stick it into our second derivative, which is a function of t. So we get now, of course, this squared term is going to be positive, so you would get a negative, correct? Everybody agrees that we get a negative of some sort. Okay. So we know for values of t between -infinity and -2, the second derivative is negative, so concave down. Okay. Maybe choose 0 from here. So that would be also negative. Except I messed, didn't I? Right? I didn't mess up. It's just that this is a cubed, and I for some reason wrote squared. So that's cubed. So that turns out to be positive. Okay. There's a double negative in the denominator, so concave up on that interval. All right. Now this would be negative. If you do your little sign analysis. So concave down, and I guess finally test point, let's say +3 this time. Positive, positive, positive. 3 minus 2 is positive, and this is always going to be positive unless it's 0. Oh, sorry, that's going to be still positive. Okay, so all positive, still positive, so concave up. Okay. So the curve is concave up for t's in negative infinity to negative 2, together with 2 to infinity, and concave down. Okay, for t between negative and positive 2. All right. Cool. What else could they ask you? Well, that's pretty much it, right? So horizontal, vertical, tangents, equation of tangent line, and maybe, you know, where the curve is increasing, decreasing in terms of the parameter and concavity. Okay.
I have a question.
Yes.
I was trying. Can you explain more of this concavity up on this line, number line here? Why you chose -2 and 2, and why you chose negative?
Because we're finding the critical points, right? So when is this? So we're looking at the second derivative, and we know the second derivative is either going to be, what are the options? Undefined at a value of t, or if it is defined, so you get a number out, what are the only possibilities for a number? Positive, negative, and 0. So what we're doing when we're looking at the second derivative, we're finding the cases where it's undefined or where it's 0. So it's where your cut points are, right, as applied calculus would call them, are where the second derivative is 0, which it's never 0, or undefined. And that second derivative is undefined when the denominator is 0 at t equals 2 or t equals -2. And then everywhere else, right, once you eliminate those two possibilities for the second derivative, it's 0 or undefined, everywhere else it must be positive or negative. So we just can choose test points from the remaining intervals to plug into the second derivative to check whether it's positive or negative. Okay.
Okay.
But I'm going to go on for the sake of time. I know it's bad form, but you can always drop in the tutoring lab in the McDermott library to get clarification on that one.
Okay.
Okay. Cool.
Can you pull the screen down a little bit?
I didn't catch that.
Yeah, can you pull the screen down a little bit? There's something I want to write here.
Put it down like that?
Yes. Okay. Okay. That's fine.
How much time do we have? All right, so polar So differential calculus of polar curves. I'll just keep a simple example. Did I forget something? I forgot to write down differential equations, didn't I? All right, so let's look at the formulas for when we're dealing with polar curves, which is just a special case of parametric. Right. So again, R is a function of parameter theta, and we know that X is R cosine theta, Y is R sine theta. So really we could think of this as a product, right, of a function of theta with a function of theta, product of functions of theta. And then if you then apply the parametric formula for the derivative of y with respect to x, you can use product rule to derive that this should be dy d theta, so there'd be r prime sine plus r derivative of sine is cosine. On bottom, we have the derivative of x with respect to theta. So again, if you'd like, if you ever forget, just use product rule on that. You get r prime cosine. Oh, I'm using dot notation. I apologize. Anybody taking physics or looked at physics? So I should write prime instead. So that's r prime. That means derivative with respect to the dot is so much clearer. That means derivative with respect to theta. And then we have plus r, and then the derivative of cosine is negative sine. That's why there's a minus in the formula in the denominator. Okay, but anyway, we have a formula if you just want to memorize it or whatever. And the papers are getting lost in the shuffle, so I'm just going to make one up, a very simple, something like 2 cosine theta. We can anticipate where the horizontal and vertical tangents are, right? If you know that polar curve, we expect horizontal tangents here and here. Does anybody know what angles, which values of theta that happens? If you had to guess. It's going to happen at pi over 4 and 7 pi over 4. Just to anticipate. Not 7 pi over 4, 1 second. Ooh, so, yeah. 3 pi over 4, believe it or not. First two units. And then we anticipate some vertical tangents as well, probably at 0 and pi. Okay. But we don't need to guess, right? We can just use our formula for dy dx. If you'd like dy d theta, we can compute. Oops. And then dx d theta. All right, r prime times sine. R times cosine. Right. And then dx d theta, r prime, cosine, minus r sine. All right. All right, so when is dy d theta equal to 0? Well, if you look at that, I believe that's 2 times cosine squared minus sine squared. So that's where cosine and sine have equal absolute values. That's when that's 0. Or if you'd like, just use your trig identity, where cosine squared minus sine squared is cosine double the angle. Right? And when is cosine 0? It's equal to 0 when the argument, and I mean the whole thing that's inside of cosine, is equal to an integer multiple of pi. And I should have just limited this to like between 0 and 2 pi or something. Really, 0 and pi is sufficient, but so maybe we can just list a few, right? So you get 0, pi, 2 pi, I guess 3 pi, 4 pi, and so on and so forth. So dividing by 2 allows us to solve for theta. Wait a minute. I'm wrong, right? When is cosine equal to 0? Well, what can I do, you know? I've only been doing this for like 25 years, so. All right, so let's start that over again, huh? Cosine is 0 whenever the argument is, let's just list a few, pi over 2, 3 pi over 2, and so on and so forth. And because we're looking at interval from 0 to 2 pi, that's probably too good already, right? It's beyond 2 pi, so. And then we divide by 2. To solve for theta. So it looks like quarters of pi. Okay. All right. When is dx d theta equal to 0? Well, here's dx d theta. So it looks like those will double up. Okay, so I would use again the identity. Right, so that's -2 sine double the angle theta. So when is sine equal to 0? That's when the argument is an integer multiple of pi. So let's just list some. And probably don't need to go beyond that. Divide by 2 to solve for theta. All right. All right, so now all right, so when do we have horizontal tangents? Well, that's when dy dx is 0, if you'd like, that's when dy d theta is 0. And dx d theta is not. It's for sure we have horizontal tangents. If both are 0, we would have to take a limit as theta approaches the troublesome value of theta. Okay. So we see that we would have horizontal tangents when theta is one of these. Okay. And those values of theta do not make dx d theta 0. So all those, but there's only 2 unique ones. I don't know if you see that or not. Right. There's only 2 unique ones. And what if they wanted the point where you have the horizontal tangents in r theta form? How would we do that? Well, we know theta. And r we can find because we have an equation that tells us what r is in terms of theta. So that would be square root of 2. So when theta is pi over 4, we would go out square root of 2 to get to this point. Okay, and what's the equation of that horizontal tangent? Well, that's when y is constant. So what would y be? Well, it's y is r sine theta, so at pi over 4. You get 2 times cosine pi over 4 for r, sine of pi over 4. So you get y equals 1. Okay, that's the equation of that horizontal line. And then you do 3 pi over 4. It's a point in this form when theta is 3 pi over 4. I believe r would be negative 2. Is that correct? Yeah. And the equation is going to be y equals negative 1. All right, so this is a good reminder of what's happening, why r is negative. So in our polar graph, if we do an angle of 3 pi over 4, so you have the first quarter of pi, second, third quarter of pi, and then the fourth quarter of pi. So theta is 3 pi over 4. Right, so that theta in a sense is like if you play Twister, you have that Twister arrow thing. So theta is kind of pointing in the positive radial direction. And since r is negative, we would go in the opposite direction, right? So we would end up actually at this point in the circle. So that makes sense. And what would you would find is that for the rest of these, you're just repeating the same horizontal tangents. So for example, if theta were 5 pi over, well, if say theta is 5 pi over 4, what would happen? What's cosine of 5 pi over 4? It's negative 2, right? Right, so which point would that correspond to? Well, you go a quarter of pi, 2 quarters of pi, 3 quarters, 4 quarters, 5 quarters of pi. So the positive radial direction is pointing in the third quadrant. Since r is negative, you would actually end up back over here, if that makes sense. So you just keep repeating. And then you have vertical tangents. And we should move on to polar curves. It's 3 o'clock. All right. So vertical tangents. Okay. Dx d theta is 0. And dy d theta is not. And so that would happen at these values of theta. What did we say it was? Dx d theta 0. Oh, okay. Yeah, so there's only going to be 2 unique ones. These, and we can maybe see what happens at pi to see how we repeat. All right. So what's the point? So when theta is 0, we have a point written polar coordinates. Theta's 0. So remember that r is 2 cosine, right? So r would be 2. And we kind of, if we know what that looks like, it makes sense. When theta is 0, we go out 2 in the positive radial direction because r is 2, and we end up right there. And that's we have a horizontal tangent there, and the equation of that would be x equals 2. Again, we know that because x is equal to r cosine theta. And r was 2 cosine, so 2 times 1, yeah. What did I just write? Oh, theta, okay. So when theta is pi, r would be -2. And the equation of the tangent, or vertical tangent, would be x equals 0. Okay. That's not what I needed. All right, theta is pi. So our positive radial direction is in the negative x direction there. But r is -2, so hold on. Wait a minute. What did I miss? Oh, I missed pi over 2. Thank you, thank you. So theta would be, or r would be 0. Okay, my bad. Yeah, I forgot that theta could be pi over 2. All right, well, and so x would be r, which we know is 0 at pi over 2 times cosine. And it's 0 in a couple counts, right? X equals 0. And then you'd start repeating. All right. Whew. If anybody wants to take a break or something, I might take just a minute or two. I'll be back at 3:10. How about that?
What time?
3:10. So in 3 or so minutes.
Okay.
Okay, so we're going to be looking at polar curves, an area. And for polar curves, remember the formula for area was half of r squared d theta. And the bounds, of course, are theta values, as you're integrating with respect to theta. Okay, so let's start with some simple ones. Let's just call this problem 10 because I lost count. Does anybody know if you have a rose curve that has like sine and you have 2 theta, right? So that's an example of like you have some amplitude and then sine of an even integer times theta. Does anybody know how many petals that has, that rose curve? And this is when it would have double the number of petals when this is even. Like, so for example, this curve would have 4 petals. Let me quickly graph theta versus r in a rectangular coordinate system. Does everybody know what sine of 2 theta or sine looks like, right? And since it's sine of 2 theta, here's one period of sine, here's another period of sine. So you remember what. All right, so this would be 2 pi, 4 pi, except we'd be then divide everything by 2. I'm just trying to get a sense of what this should look like. So this should be pi over 2. This is pi. This is 3 pi over 2. And this is 2 pi. Okay. So let me translate that into a curve. So as theta goes, so notice that as theta goes from 0 to pi over 2, r goes from 0 to some amplitude and back to 0. And that's going to define a petal, right? So as theta goes from 0 to pi over 2, r starts at 0, goes to some maximum value, and comes back. So that's a petal. All right, so and as theta goes from pi over 2 to pi, in terms of the angles, r goes from 0 to -1 or some amplitude, negative amplitude. So that would give you this petal. Remember, you're going the negative radial directions. So in a sense, this guy matches this petal. All right. Ooh, now I could, in this petal, so theta goes from pi to 3 pi over 2. R goes from 0 to 1 back to 0. So that defines a petal as you go from r equals 0 back to r equals 0. And then theta goes from 3 pi over 2 to 2 pi. Goes from 0 to negative, so negative radial direction will give you that. And then you start repeating. Okay, so you get 4 petals. Anyway, but how do you get the, let's say you want the area of these petals. What do you want to do? Well, you want to define the bounds for, let's say, a single petal. And if you anticipate there are 4 petals, you would just find the area of one petal, quadruple the result. Okay. So how do you find the bounds for a single petal? Like we noticed, it's two consecutive values of theta where r is 0. Okay, so you would set r equal to 0, and you would say sine is 0 whenever the argument is a integer multiple of pi, and so on. Then divide by 2. I can stop, right? Because I see two consecutive values of theta where r is 0. So that should define a single petal. So I know, do you know how to find the number of petals? Another way to find the number of petals? Where does the tip of a petal happen? Well, it happens when r is maximized, right? Because the tip is the farthest away from the origin. So that's when r is maximized. So if you'd like, you can find the tips by finding the derivative or calculus 1, derivative of r with respect to theta, set that equal to 0. And we know cosine is 0 whenever the argument is something like pi over 2, 3 pi over 2, and so on. Right. So it even seems like it visually, correct? So at pi over 4, we have a tip. 3 pi over 4, we have a tip of a petal. 5 pi over 4, 7 pi over 4. And then notice 9 pi over 4, you start repeating. So you know you have 4 petals if you ever forget. Just general advice, I guess. Call it my life advice. So we're after the area of all the petals, but knowing there are 4 petals, we're simply going to use our area formula in polar. We're just going to integrate from two consecutive values of theta where r is 0, and then we have r squared. R happens to be sine 2 theta. So this is a single petal. So if you remember that sine squared, you have an even power of sine or cosine. We have to use, if there are, I should say, no odd powers of sine or cosine, we have to use the identities, the power-reducing identities. Right, so sine squared, we're going to reduce that to 1/2 minus 1/2 cosine double the angle, so that we can integrate. So we're going to get pi over 4 at the upper bound. And sine here, you get sine of 2 pi or sine of 0. Again, those are integer multiples of pi, so sine is 0 there. So we're just going to get pi over 8. So for all the petals, the area would be 4 times a single petal, so pi over 2. Okay. So and this is also true for cosine when you have a rose curve. If you have sine or cosine of an odd integer of theta, how many petals are you going to have? So this is, I'm writing this for sine, but it's true for cosine as well. You have an odd integer multiple of theta, you're going to get exactly that many petals. So we anticipate that we're going to get 3 petals. I'm not going to maybe draw it out, but maybe we can find 2 values of r, or sorry, 2 consecutive values of theta where r is 0 to single out a petal, and maybe find the largest values of r to find the tips of the petal to confirm we have 3 of them. All right, so when is r 0? That's whenever the argument of sine is an integer multiple of pi. So 0 and pi over 3. But those are 2 consecutive. So then take the derivative, set it equal to 0 because you're finding maximum values, I guess. Cosine is 0 when the argument is one of the following. All right. All right, so now we can get a sense. You know that when you have a polar curve and it's only just involves a sine, there's symmetry about which axis? The vertical. Right. And when you have a r as a function of just something cosine, then you have symmetry about the horizontal axis, just to, if you want to take advantage of that. But so at pi over 6, what is r equal to? That's going to be pi over 2, so that our sign is 1 there, so 2. So we go out to pi over 2 is going to be negative 1. So pi over 2, the angle, the radial direction, positive is up, but r happens to be negative, so we go down 2. 5 pi over 6. How did I get 5 pi over 6 again? Oh, okay, I see. So that's going to be where sine is 1, so 2. So when the angle is 5 pi over 6, we go out 2 in positive radial direction. So. And notice what happens when you try theta 7 pi over 6. Oops, sine. You get 7 pi over 3 because it's 2, sorry. So that's going to be how many halves of pi? Well, we're going to be back over here, and r would be negative 2. So you're actually, hold on. It's 3. Seven pi over 2. Yeah, so it's 7 pi over 6. Sorry, that would be like this angle. r is -2, so you actually end up going instead of the positive radial direction, you go in the negative radial direction, and you end up at that same point. So you start repeating. That's what I'm saying. Okay. So again, just to confirm, we have 3 petals, right? And we said that theta is 0 at, r is 0 when theta is 0. And the next time it's at pi over 3. And the tip happened at pi over 6 the first time. So that's a petal. And we know there's 3 of them. So of course we're just going to find the area of 1 and triple that result. I won't do that integral, but the area of a single petal, to set it up, half integral from 0 to pi over 3, 2 consecutive values of theta where r is 0, and then r squared. And then you would triple that result to get all petals, right? Unless they ask for a single petal. Okay. So let's look at a limicon, I suppose. If I could find it. If not, I'll just have to improvise. Yeah, it's limicon. Okay, so we're going to do a limicon example. So let's suppose r is 2, let's say square root of 2 plus 2 sine. Why not? Okay. So is the symmetry for this polar curve going to be on the along the vertical axis or the horizontal? Vertical, it's a sine. And what's the largest value of r without even doing any calculus? I mean, we kind of know when this is maximized. It's whenever sine is maximized, right? What's the maximum value of sine? It's 1. So the r, and when does that happen? So r max, if you will, is square root of 2 plus 2 when theta is, well, whenever sine is 1, so that at pi over 2. So that would be the furthest extent. It's not the way I usually graph it or think about it, but just 1 second. So we know the graph of sine, and then you multiply that by 2, so you change the amplitude by 2. I mean, you magnify the magnitude by 2, and then you add square root of 2, so that's going to bring the whole thing up by square root of 2. So it should look something like this is just square root of 2. Okay, so you see how if I graph this equation, this polar equation, but in a rectangular r theta system, part of that graph dips below the horizontal axis, so that's going to be where r is negative. And when does that happen? Well, you'd want to find where r is 0, right? So set r equal to 0, solve for theta. And that looks like sine is equal to negative 2 over 2. We know that happens when theta is 5 pi over 4 and then 7 pi over 4. All right, now we can try to graph it. So as theta goes from 0 to 5 pi over 4, where is that? Where's the maximum extent? At pi over 2. So we start somewhere over here. Okay, so r starts at some square root of 2, then increases to its maximum value, then goes back to square root of 2 when theta is 5 pi over 4. Nope, over here at pi. Okay, and then as theta goes from pi to 5 pi over 4, r goes from some positive number to 0. So that's going to do this, right? And then notice that between pi over 4 and 7 pi over 4, r is negative. So r starts at 0. And then the radial directions or positive directions are this way for those angles, but we're going, r is negative, so we're going the opposite direction. All right, so I forgot how to graph that. Apologize. Okay. Right, so that inner loop corresponds to this little dip below the horizontal axis. All right, so what if you want to find, right, so we found where the values of theta where r is 0, and if they ask for the area of the inner loop, you would have to find the correct bounds, right? The inner loop of this limicon. So what can you do if you don't know the graph exactly? Well, you can just choose test points for theta to see. So let's say theta goes from 0 to 2 pi. We found that r is 0 at these two angles. And we know that a limicon, well, I shouldn't say that. Right, you can just choose a test point here and then maybe one over here, right? You already kind of know that at pi over 2, we're at a maximum value. So that would be not the inner loop, but the outside loop. So it looks like all this stuff would coincide with the outside loop. Right? So the outside loop happens whenever theta is in here. Oh, come on. And the inside loop would occur in here, if you choose a test point, I guess. Kind of like this guy. So you would have to realize that we want to integrate for area from 5 pi over 4 to 7 pi over 4. You just have to pick the right interval of theta to coincide with the inner loop. And then, of course, r we square using our formula and integrate. And I don't know what that is, but okay. But what if instead they wanted the area that's inside the limicon but outside the inner loop? Right? What area are they talking about? Well, they must be talking about this little thing. So what kind of picture math do you see being done here to get the area that's inside our limicon but outside the inner loop? I see the math being find the area inside here and then subtract the area of the inside loop, right? So it's kind of like all this minus the inside loop gives you the desired area. All right, so I hope that makes sense. So there's going to be some subtraction going on. All right, so what are the bounds? Well, we already know the bounds for the inside loop. We already have that integral. But what are the bounds to get the total area inside this limicon? What do you think? Of course, we could have used symmetry, but to half our effort, maybe. I don't know. It's not really half the effort, but it really isn't. I think it's like 95% the effort. But. So you want to integrate. We see that these angles were 5 pi over 4 and 7 pi over 4. But we want to integrate over a connected interval of theta, a contiguous interval of theta, if that makes sense. So we can't integrate from 7 pi over to 5 pi over 4 because you're actually integrating from here to here. So you would end up retracing the inside limicon. So you'd want to realize that another way to express this angle, of course, is negative pi over 4. So that way you can integrate from negative pi over 4 to 5 pi over 4, right? So it's kind of like, it's a periodic function. So if you extend this further, oops, come on. This interval would be give you the same picture as this interval, if that makes sense. Right. So to get the outside, you would have to know that we want to integrate from negative pi over 4, where that kind of outside curve starts as a negative angle, and then to 5 pi over 4 where it ends. And again, of course, r squared. That's a basic, and then you subtract. Okay. So really, I'm more concerned about setting up the bounds. All right, let us do some more. So 12. All right. So did we say, what number was that? 12? Okay. 13. How do we want to do this? Or which one do we want to do, rather, right? Yeah, let's do the basic picture math one. So we want to do 2 curves? Yeah, let's do 2 curves. So suppose we have 2 easy circles, like let's say 3 cosine and r equals 3 sine. Okay, does anybody know what the cosine looks like, and how many, if you'd like, if you considered it a special case of polar curves, how many petals would that have? Of rose curves, sorry, special case of rose curves. It'd be a sad flower because all its petals are missing but one, right? This is odd. So you have one petal, and it turns out, I mean, you can, again, so I remember, so you have a, you know, the basic graph of cosine, right? So we see that as, and this cosine has amplitude -3. So it looks like as theta goes from 0 to pi, r goes from 3 to 0. So, and it happens to be a nice, perfect petal, circular. And then as theta goes from pi over 2 to pi, r goes from 0 to -3. So the positive radial directions for those angles are that way, but we're going in the negative direction. So by the time you get to pi, and your r is -3, instead of coming out here, you come back over here. So you would have covered the full circle just by going from 0 to pi. I think I'm trying to answer somebody's questions in chat, somebody's question in chat. So the full circle happens as you go from 0 to pi. So be careful with a circle like that, right? It's not from 0 to 2 pi. If you go from 0 to 2 pi, you're double covering the circle. Okay. All right. And then we have the same story for sine, except now the symmetry would be about the vertical axis. So here's a picture of sine, basic period. Right. And that's you see that you get a full petal, if you will, as theta goes from 0 to pi, because those are two consecutive values of theta, where r is 0. So at 0, r is 0, at pi, and then at pi over 2, we're at a maximum. Right, so from 0 to pi, right, and then from pi over 2 to pi, we go from 3 back to 0. So this guy corresponds to a full disk. I can't lie. I like shading this stuff. I apologize. Okay. All right. So what are the possible questions be then? Well, what's the area that's common to both curves? Right? That's one question. Or inside both curves. The area of the region common to both curves. Right? So what would we have to do when we have two different polar curves? We'll figure out where they intersect, right? So we would just set the two things equal to one another. And we're just kind of interested when sine and cosine are equal. Or if you'd like, where tangent, well, they're equal. I don't want to say tangent because, right. Okay. So where are cosine and sine equal? Those where the angles are pi over 4 and 5 pi over 4 and so on and so forth. So that first intersection happens when theta is pi over 4. They both go through the origin, but they're just at different values of theta, if that makes sense, right? Okay. So if you want to find the area that's in both circles, it's inside both loops there, we'd have to break this up into two separate integrals, d c y, right? When we do the polar area stuff, you want to kind of cover the region in a polar fashion. So start at the origin, let theta increase and sweep out that region like rays of the sun or something, whatever, you get this petal. And notice that which curve you're drawing your radial lines up to, right? So from theta equals 0 to theta equals pi over 4, you're drawing your radial lines up to the circle that's yellow there, right? So then you remember which equation gave you that circle, right? So we're going to integrate using our formula for area from 0 to pi over 4, but we're only drawing our radial lines up to the circle corresponding to r equals 3 sine theta. So maybe it's good to label those, right? And then we can use symmetry. Well, be careful, because if the circles are of different radius, radii, then we couldn't do that. So let's just set it up. And then to that you would add, right? And now you would let, you go from pi over 4 and you sweep out that region, and notice you're drawing your lines up to the other circle, corresponding to where r is equal to 3 cosine theta. And how do you know when you finish the petal? Well, that happens at, right, for this curve, that piece is finished when r is 0 and you're back at the origin, and that happens when theta is pi over 2, right? So you would integrate from pi over 4 to pi over 2, but you're using the cosine because we're just drawing our radial lines up to the cosine graph. And you use your cosine. And you're adding them up, right? Okay. They could also ask, find the area that's inside the first curve but outside the second, right? So they do this because you could then you're forced to kind of recognize which equation corresponds to which graph. So the question might be area inside first curve but outside second. Nice. You guys are brave for sitting for 3 hours. This is, I would have turned off this YouTube video a long time ago. Okay. Right, and that would give you the first curve. Oops, was cosine. And the second curve. Right, so then, and I don't know, do they force you to graph, or do they just give you the picture? Like on the review, they just gave you the picture. Oh, okay, so, right. But anyway, you still have to recognize, right? Because you have one circle and the other. You still have to recognize which equation corresponds to which curve. But of course, the region they're talking about is like, right? So the one that's symmetric about the vertical axis must be the sine. The one symmetric about the horizontal axis must be the cosine. And they said they want the region that is inside the first curve, so that's the cosine, but outside the second, so the sine. So they must be talking about this business. Oh, that's kind of dangerous. So I'd probably break this up into two kind of problems, right? I would find, let's say, this area. That's the hard one. This one is easy. That's half a circle, but you don't have to know that. We can just find the bounds for that. So let's do the top first, I guess, because that's the more interesting one. All right, so what's the picture math there? The kind of shaded areas math. is we'd probably want to find, or just maybe know, the total area of a half circle, right? And then take away the area. So this would be a tough problem. I don't know. I'm regretting my life choices in choosing this problem. Okay. Subtract that area to get the area that you want, the top. Yeah, that would be a rough problem. Right. So what are the bounds to get this area? Well, we're using the cosine curve. Okay. So we would need to know the value of theta when we're over here, and that happens to be 0 because that's the maximum extent, maximum value for cosine is theta 0. And then when does this semicircle end, even if you don't know it's a semicircle? Oh, that's when cosine is 0, because we're back at the origin. Cosine is 0 at pi over 2. And then you would square r. Notice we're drawing our radial. If I cover that region in that polar fashion, polar radial sunny fashion, I'm drawing my lines up to the cosine graph. And then take away this area, and I guess in this case I would use symmetry, but I would just double and just find this area. So 1/2, 0 to pi over 4, because we already did that. Now we're drawing our radial lines up to the sine graph. So, okay, and so that will give you that area, and then you would have to add in this area, which well, I'm stupid. I could have just found the area of the total circle and then take away the intersection, if that makes sense. I could have done that. That would have been more instructive and faster, right? Right, so I would be integrating it. So this is a good problem in the sense that we can emphasize that for this type of curve, to draw the full circle, you just have to go from 0 to pi, and we know that because we pinch off a pedal, if you will, at 2 consecutive values of theta where r is 0, and that happens at pi over 2. Or if you like, negative 2 pi over 2 and pi over 2, right? So we could have just integrated from negative pi over 2 to pi over 2, and then taken away the common area. All right. Much time? We have 5 minutes. So I do need to cut it off after this problem. I did forget to look at differential equations, separable differential equations with initial values. And we did not look at sequences either. So I might, when I typeset these problems, I'll just include that, but you already have practice, so. All right, so let's do another one. And then we can stop. A little more difficult one, perhaps. All right, so we have two curves. This is number 14. That's way too similar there. So let's do this. R is, yeah. Two times square root of 3 cosine theta. On the other hand, R is 3. So this would be a circle. this would be another circle, centered at the origin. Yeah, all points which are a distance of 3 away from the origin. I don't know exactly where, but I have a feeling it's there. 2 times square root of 3, that's, hold on. That's bigger than 3, obviously, right? Right? Okay, let's check. So I'm claiming that 2 times square root of 3 is bigger than 3. Let's square both sides. Yeah, okay, checks. Probably not by much. So we have a circle. Whoa. All right. So we want to see where the, and we might be looking for the area inside the first curve, but outside the second, or we might be looking for the area that's common. But let's just do inside the first curve, but outside the second. They're talking about this area. Right, we'd want to figure out where these guys intersect. So cosine, we set them equal to one another, try to solve for theta. Does anybody, that's square root of 3 over 2. So when is cosine square root of 3 over 2? At pi over 6, right? And at negative pi over 6, let's say. Okay. All right, so to get the shaded area, well, we'd first want to probably get the full area, right? When we find areas, we always sweep the region out, starting at the origin, go outward, and notice which curve we're hitting. We're hitting this curve, which corresponds to the cosine. Right? All right, so we would get that. So integrate from negative pi over 6 to pi over 6. Use our form. We can also use symmetry if you'd like, right? So we can just find half the area and then double the result. Let's do that. So we can integrate from theta equals 0 to pi over 6 and then double the result. And it's 2 times and then the formula for the area. And we're using the r corresponding to the farther away r values. So. Okay, and then we're going to take away the inside stuff. So, so when we sweep out that region, notice we're just drawing our lines up to the curve corresponding to the circle centered at the origin of radius 3. So that's where r is always 3. Let me close these because it looks like there's... All right. Again, we're using symmetry, so we're going to double, since we're only finding half of what was asked, and times the formula for the area, 0 to pi over 6. And now we're using the circle, so that r is simply 3. So r squared becomes 3 squared. And then you integrate. All right. Well, again, we forgot, if you have any outstanding questions, like if you want to see a differential equation, I'll stay behind. If you want to see some sequence or something, I'll stay behind. It's 3 hours. It's too long to be sitting in one place. Right? Right. So thank you for people who stuck with it online. I appreciate it. I'll see you in the tutoring lab. I should have the video up of this by tomorrow morning. Sure. What can we do to make these shorter? What do I have to do?
Tell our teachers not to give us so much content and other semester.
Oh, so you want me to like change the whole curriculum? Oh, okay, not a problem. Oh, all right. All right. Okay, Afros, I lied. I was just being nice. I don't want to stick around for sequences. I need to go. I have an obligation, so I'll see you in the lab.
Hey, I just had a couple questions. So, um, yeah, are we going to get like a PDF version of the work you did here? Like, are we going to get a PDF file or some access to this work that you have done, or it's just going to be the video?
Probably just the video. I'll post the PDF of the problems,
All right.
and if I'm good, I'll also post the answers. But if not, not the
Okay.
step-by-step
Gotcha.
solutions.
And do you know if we will have a final exam review similar to this?
I doubt it.
No.
Not a final.
Probably not. Yeah, I don't think we ever had a final review like this, so yeah. Okay, well, thank you for the review.
You're welcome, man. I'll see you in the lab.
Yep.
How did they get the wrong room? Snip. Oh, you're welcome. Thanks for sticking around. You too.